In this video, we're going to study some properties of the integral. The first property is what we call linearity. The integral is linear. That means if I do the integral of c times f of x, this is equal to c times the integral of f of x. And the integral of f plus g of x is going to be the integral of f of x plus the integral of g of x. The integral is linear. Now, monotonicity tells me that if f is less than or equal to g, then the integral of f is less than or equal to the integral of g. And then additivity, it's additivity with respect to the integrals over which we are integrating. So if we have that c is strictly between a and b, then the integral from a to c of f plus the integral from c to b of f is equal to the integral from a to b. Okay, so you see we're just adding the intervals. We'll have from a to c, from c to b. That would give me the integral from a to b. Here then, these statements are not yet very rigorous. We're not stating any hypothesis or anything. So that we're going to do throughout the video. But here just have a quick summary of the properties that we're going to be talking about. So we're going to focus on the linearity of the integral first, and this is the only property for which I'm going to give a proof. And this tells me the following. If I know that f and g are both bounded on the interval ab, I know that f and g are both integrable on ab, and c is a real number, then the function c times f and the function f plus g are both integrable on the interval ab, and we have that the integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx, and the integral from a to b of f plus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And here I'm only going to prove b, so that the integral of the sum is the sum of the integrals, and I'll leave for you to do proof of a. Before we do that, though, we're going to prove a few lemmas that will help us write down the proof. The first one tells me that if I know that f and g are both bounded functions on AB, not necessarily integrable, then we know that the supremum of f plus g of x over the set of the x's that are in the interval AB is less than or equal to the supremum of f of x plus the supremum of g of x. And this proof is just playing around with the definition of supremum. You see, if I fix a point x in the interval AB, then we know that f of x is less than or equal to the supremum of f of x for the x in the interval AB, and g of x again is this less than or equal to the supremum of the g of x. Okay, therefore, if I add them up, then I know that f of x plus g of x is less than or equal to the supremum of f of x plus the supremum of g of x. And this is true for any x that I pick. Okay, then that tells me that the supremum of f of x plus the supremum of the g of x is an upper bound for the set f of x plus g of x such that x is in the interval AB. Okay, so that's an upper bound, and we know that the supremum is the least upper bound. That means that the supremum of f plus g of x is less than or equal to the supremum of f plus the supremum of g. So we have the supremum of f plus g is less than or equal to the supremum of f plus the supremum of g. And this is going to be very helpful. Okay, then we have lemma number 2. Tells me that if I have that f and g are bounded but not necessarily integrable, the upper integral of the sum is less than or equal to the upper integral of f plus the upper integral of g. And it tells me also that the lower integral of f plus g is greater than or equal to the lower integral of f plus the lower integral of g. Let's say this is true for any bounded function. They don't even have to be integrable. And how do we prove this? Okay, I'm going to prove the first one, the one about upper integrals, and I will leave the other one for you as an exercise. So suppose that we have a partition of the interval AB. Then the p upper sum of the function f plus g is the sum from I equals 1 to n of the supremum of f plus g x over the interval xi minus 1 to xi times delta x, which is the length of that interval. Okay, but now we showed already that the supremum of the sum is less than or equal to the supremum of f plus the supremum of g. So that's what we're going to be using here. Okay, but now if you look at it, the first term here is just what? Well, is the p upper sum for f, and the second term is the p upper sum for g. So we have that. You have the p upper sum for f plus g is less than or equal to the p upper sum for f plus the p upper sum for g. Good. So now we're going to fix an arbitrary epsilon, and since the upper integral is the infimum of the upper sums, that means that, well, the upper integral is the greatest lower bound. So that means that if I add epsilon over 2 to the upper integral, that is no longer a lower bound. So I can find a partition Q such that UFQ is less than the upper integral of f plus epsilon over 2, and the same thing for U of GR is going to be less than the upper integral of G plus epsilon over 2. So here we're just using the definition of the upper integral is the infimum of the upper sums combined with the definition of infimum. Okay, so we have these two things over here, and then we're going to take P to be the union of Q and R. Then UFP is less than or equal to UFQ, right? Because P is finer than Q. But then we just said that this is less than the upper integral of f plus epsilon over 2. And then we're going to do the same thing to show that UGP is less than the upper integral of g plus epsilon over 2. Okay, now what happens? Well, then the upper integral of f plus g is less than or equal to the upper sum of f plus g, right? Because remember, the upper integral is the infimum. So in particular is a lower bound. So for any partition P, this is true. But then we showed that UF plus GP is less than or equal to UFP plus UGP. But then this is less than the upper integral for F plus the upper integral for G plus epsilon over 2 plus epsilon over 2, which is epsilon. But now epsilon here was an arbitrary positive number. So this tells me then that the upper integral for f plus g is less than or equal to the upper integral of f plus the upper integral of g. And that completes the proof of the lemma. Okay, this was a long proof, but it will pay off. Now the proof of the theorem will be easier, but first we will have to show the same thing for the lower integrals. So we can have the same methods. We're going to conclude, indeed, that the lower integral is greater than or equal to the lower integral of f plus the lower integral of g. I'll leave for you to complete the details of this one. Okay, so now that we have these, now let's go and get to a theorem. So I'm remembering that if we know that both f and g are integrable, then that means that the upper integral of f is equal to the lower integral of f, and that the upper integral of g is equal to the lower integral of g. Okay, now the previous lemma tells me that the upper integral of f plus g is less than or equal to the upper integral of f plus the upper integral of g. But now, the upper integral of f is equal to the lower integral of f, and the upper integral of g is equal to the lower integral of g. So then this is equal to the lower integral of f plus the lower integral of g. Okay, but then the previous lemma tells me that this is less than or equal to the lower integral of f plus g. Okay, so then if we look at it, it's telling me that the upper integral of f plus g is less than or equal to the lower integral of f plus g. Good. But we know that always the lower integral is less than or equal to the upper integral. So if we combine these two inequalities, that forces me to have that the lower integral of f plus g is equal to the upper integral of f plus g. And that means that f plus g is integrable. And now, you see, we have the biggest inequality here that tells me that the upper integral of f plus g is less than or equal to the upper integral of f plus the upper integral of g, and that is less than or equal to the lower integral of f plus g, because the left and the right hands are equal. It will force everything to be equal, and that's why this inequality now will go through that inequality that will give us exactly the results that we wanted to prove. Okay, and now I'm going to just mention the formal statements of the other two properties, but I'm not going to prove them. If we know that f and g are bounded functions on the interval ab, I know that f and g are both integrable, and that f of x is less than or equal to g of x for all x in the interval ab, then the integral from a to b of f is less than or equal to the integral from a to b of g. And then additivity of the integral is that if I know that f is a bounded function on the interval ab, and I know that c is strictly between a and b, then the function f is integrable on the interval ab if and only if it is integrable on ac and in cb. In that case, the integral from a to b of f is equal to the integral from a to c of f plus the integral from c to b. So those are all the properties that I really want to make sure that you remember. And if you want to give it a go and try to prove these two, just try it. And if you have questions, please let me know.